Good morning, everybody. My name is Stuart Halloway, and it's such a pleasure to be here in RuPy at Budapest. I want to thank everybody involved with getting this together. I've had a terrific visit, made a lot of new friends that I hope will be lifelong friends. I'm going to be talking to you today about collaboration between client-side developers and server-side developers using the JavaScript programming language. And so I'm going to start by looking at a JavaScript framework called Pedestal. And what Pedestal does is it completely decouples client-side application development from server-side application development. How many people were in Jake's talk yesterday when he talked about the importance of reproducible results in science? He sort of headed off, took a right-angle turn in the middle of his talk. I want to back that up. I think it's incredibly important to have reproducible results. And the way that you get reproducible results is actually by having immutable, persistent data everywhere. And so the way that Pedestal works is that the UI drawing is done step by step. You can see the UI drawing at the top of the screen, and you can actually play the UI drawing forwards and backwards. And so every step in the development of the UI is an immutable value. And developers are able to build the client side of the application without being connected to the server side at all. Just as Jake talked about simulating how the telescope was going to work without having a telescope at all. And so this provides a ton of power, and of course the follow-on ideas are pretty terrific as well. You could do things like have a user filing a bug report, click a button to save the state of the UI, and send the state of the UI to you. And that state of the UI would not only contain where they were when they got in trouble, but also the series of steps they took to get there. And you'd be able to replay that UI without it being connected to any server to get to the same point that the users were in. But actually, this is not the talk I'm going to give today, so I'm going to close this window now. I'll get rid of that. Actually, what I'm going to talk about is a programming language called Go. And so the idea behind the Go programming language is that there are these lightweight constructs called Go blocks or Go routines. And they have a lot of the capabilities in some ways that you might associate with threads. So here, I have 3 different Go routines that are wired to buttons in the browser. And each one of these Go routines is like its own thread. One will sleep for 250 milliseconds. One will sleep for 1,000 milliseconds. One will sleep for 2,000 milliseconds. I will start the 1,000 one going. And after every time it sleeps, it's going to write blue onto the channel C. Now, it turns out you can't see it here, but in the left-hand side of the window, there's actually something that will draw to the DOM based on what's reported on channel C. So we will start to see blue appear at about once a second. And then we'll start mixing in green, which should show up about, half as often. And then, of course, we can mix in red. Now, the interesting thing about this is that this is trivial multi-threaded programming in the browser. Right? This is not server-side code. This is I write my traditional go, 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 do stuff, do stuff, do stuff, and I write as many different concurrent loops as I want. And they can all run in parallel with each other, and it's incredibly easy to work with. However, I am not going to talk about the Go programming language today. So I'm going to actually close that window as well. And I'm going to talk about Clojure. Before I do, I'm going to use every second of time available today. I will be available downstairs to take questions after, so feel free to come downstairs and talk to me at lunch if you have any questions. Also, if you have questions but don't want to talk to me, then you can tweet them at me and I will take the questions that way. So we're going to talk about Clojure from 10 different perspectives, 10 big ideas. The first important idea, is a data serialization format called Eden. And you may not have seen Eden before. Here's an example of some Eden. Superficially, it looks a good deal like perhaps JSON. And Eden defines a set of familiar primitive types that you can work with, numerics, characters, strings, and so forth. It also defines 4 kinds of collections. And I want you to learn these because you'll need to be able to read these later. So things in rounded parens are lists. Things in square brackets are vectors, which means that they have random access. Things that are in curly braces are maps. And things that are in curly braces preceded by a pound sign are sets. I will mention also at this juncture that commas are white space. And so when you are programming Eden for the first time, you probably come from what I would call a comma-dominated language, where you're forced to type commas all the time to express yourself. You will do that in Eden for a couple of weeks because it will make you feel better, and then you will quit and wonder why you ever worked in a language where you have to type commas all the time. Clojure as a programming language is written almost entirely in Eden and in the data structures that I just showed you. So hello world, if you consider it semantically, is a function call taking a single argument, the string hello world, and printing it out to the console. But structurally, it's just a list containing a symbol and a string. Everything in Clojure works this way. There's an open paren, followed by a verb, which is the thing you're going to do, followed by the arguments to that verb. So here, we see defin, the function defining function. So this says, I want to make a new function named greet. That's the function name. Greet takes a doc string to tell people what you meant to do with it. It takes a vector, which contains a list of arguments. So here we have a single argument, your name. And then it has the body of the function. The body of the function will be just calls to other functions. So here we're calling the stir function to stick things together. And notice that it's still just data. This is an important thing that we're going to come back to a couple of times. By the way, I just taught you all of Clojure. You can now read, at a first approximation, any Clojure program. Just to drive it home, I am now going to sing in a soprano falsetto all the operator precedence rules for Clojure. I'm done. One thing people often ask about Eden is, why isn't it just JSON or something like that? There are a number of reasons. I'll mention just one today. Eden is generically extensible, generically and recursively extensible. So you can define new things with pound sign name. You can assign meanings to those new things, and intermediaries who are not aware of your meanings can still process those things. So this is an opt-in thing, not a inflict torture on people who are trying to read your stuff thing. A couple of examples of this are the built-in tags inst for time and UUID for UUID literals. And the idea here is that as programmers, we're working with data, and we ought to be able to program in data literals all the time. How many times have you found yourself in a language that had a really nice set of data literals, but you really wished for one or two more? And a programming language cannot guess all the things that you might want to treat as literals. And so this is a fairly distinctive feature of Clojure that it makes it possible. So the second idea we're going to talk about is persistent data structures. In Clojure, data is not forgotten over time. Everything is stored logically in trees. Here we have one tree that's kind of rooted kind of in the middle of the slide. And when you update a data structure, you get a new data structure that points into the existing stuff. In a traditional language, this kind of behavior would be somewhat catastrophic because people might change the stuff, right? If you and I share some internal representation of a tree between each other, we could be in big trouble if you start changing it and I don't know. But these data structures are immutable, they never change. So persistent data structures are immutable. They maintain performance guarantees, so it's not naive copying to make a big collection out of another big collection. And they maintain full fidelity access to old versions of data. Why does this matter? Well, you've probably heard that because of the rapid advance of hardware, we can now afford entire kilobytes of memory locally. Does anyone actually have entire kilobytes on a device? Right? But because we're only limited to kilobytes, we use these data structures that are called transient data structures. And the idea behind a transient data structure is that you have, an array, and you make some stuff, and then you come back later and put other stuff in the array. And you have to do that because, Jesus, there's only like 10 or 12K available on the whole machine, so you had better reuse that array as many times as possible. And the consequence of using these transient data structures is pretty much that life unequivocally and everywhere sucks. Because you can't share data, you can't distribute data easily, concurrent access is a complete nightmare because I don't know when you're changing things, All data has to be accessed eagerly because it might change if you wait and access it later. And of course, caching is its own nightmare because you have to think of how long things will live before they expire. This is really great, and what this means is that we all, in our programming languages, most of us day to day, follow slavishly ideas that were really good in the 1970s. Right? The programming languages that use mutable data structures have not noticed that memory got 1,000,000 times more capacious since these data structures were developed. So this is really important, and I could, at this point, launch into a general rant on functional programming, which is really fun, but I won't. I'm going to say something else, which is at this point, you say, okay, we're going to use immutable data structures, we're going to do functional programming, but things actually change in the world. So we need a way to deal with the fact, if we're going to adopt a model that says we're going to have persistent data structures that can actually remember what happened to our information, which would be great, we still need a way to change it. And so in Clojure, the approach for doing this is called the unified succession model. And the idea here, unified, there's a bunch of different approaches that are all unified under a common shape. Succession, you never see mutable change inside things. You only see one value succeed to another value, succeed to another value. And this replaces the way that programs are built today. Programs that are built in mutable languages are basically built out of sticking together moving parts on top of moving parts on top of moving parts. And if I gave you 100 Legos, all of which could move by themselves, and told you to put them together and make something, you'd kind of have problems, right? Because you'd get 5 or 6 of them stuck together, and then one of them would decide to crawl away and do something else. And that's the way our programs work. And this makes sense if you have about 16K of memory. It does not make sense if you have gigabytes or terabytes of memory. And so the idea is that all new memory uses new places. We're never going to reuse existing things. All change is encapsulated by constructors. One way to map this back to OO is imagine a world where we really respect the notion of constructors, and that's the only way we make things. So there are no setters anywhere. That's pretty much what it is in Clojure. References then can see a point in time value and a succession of values over time. And so the idea here is that you have a series of values. The New York Yankees have these 27 players. Then they have these 26 players. Then they have these 27 players. And you could use a collection or a reference type like an atom. So an atom is an example of one of these reference types. So an atom is a pointer to 0, where 0 is some value. And then that value is now inside the reference. And then you can call a function to say, update the thing that's inside the reference. So the way things inside of references are updated is via pure functions. So from one value via a pure function to another value. And then there is some succession function that says, what are the semantics of succession? And in this case, the semantics of succession are, we want to atomically replace. This is an atom, so swap is atomically replace based on this function. Now, that probably doesn't seem terribly exciting. It seems like a lot to put a big wrapper around 0. But these wrappers can go around anything. This scales all the way up to, for example, an entire database. So in idiomatic Clojure programming, if you had a database, it would be represented as a pure immutable value. And then you would call some succession function here, transact, that would say, now give me a new copy of the entire database with whatever changes I wanted to make in that transaction. And we don't have time to talk about it today, but there is a whole boatload of these succession semantics. And all of these succession semantics are delivered entirely separately from functions and values. So you have one world, you have functions and values, pure functional programming, easy to test, easy to reason about. And then when you have to do state, you layer in these orthogonal things. The way we typically do that in OO is an unmitigated disaster because every single object out there mixes these two things. And that requires programmers to think about how to add time semantics to every single object that they make instead of getting their data right and then having a small reusable set of libraries for dealing with time. So the fourth idea I want to talk about is sequences. A sequence you could think of as an immutable iterator. So it has sort of the same relationship to iteration that these immutable data structures have to objects. And so you can look at the results of calling some sequence functions. So if I call first on 1, 2, 3, I'll get the first 1. If I call the rest on 1, 2, 3, I'll get the rest, 2, 3. And then cons, construct, is stick something on the front. So cons hello 1, 2, 3 gives me hello 1, 2, 3. And then there's a bunch of other things that are built on this. I can take 2, so drop 2 off the front, or I can drop 2. And more importantly, these things can be done lazily and infinitely. So the function call here, iterate inc 0, says generate for me the whole numbers. It says given a seed value 0, return a sequence, which is that seed value, followed by a function applied to that seed value. Inc is add 1, followed by that function applied to the seed value, followed by that function applied to the seed, or applied to the next value, and so on and so forth. Cycle 1, 2 returns an infinite cycle of the collection it's cycled over, and repeat returns an infinite repetition of the item that's passed into it. There are about 100 functions like this for working with sequences. Order of 100, more than 10, less than 1,000. I'm not making a really precise estimate here. But the point of this is that once you have this limited set of functions, you don't have to write new ones. And so a lot of busy work in coding drops away. Here's map and reduce. So range 10 gives me a range of numbers. I can then filter over them, or map over them, or reduce over them. And this is probably fairly idiomatic for a lot of people in this audience because you're used to doing somewhat functional transformations in Ruby and in Python and JavaScript. The place where it probably starts to look a little different in Clojure is that Seqs are used for everything. So if I have a collection, I process it as a Seq. If I have a directory, I process it as a Seq. If I have JSON, I process it as a Seq. If I have a result set, I process it as a Seq. The other thing, and this is really the bigger difference, is that Seqs are immutable and thread safe. Right, so these things can be passed around and composed. In general, OO is what I would call non-compositional. Right? It's actually sort of conceptually impossible to compose bigger things out of smaller things because there aren't any rules for thread semantics that you can apply. But with immutable things like Seqs, I can take small subsystems that I know to work and create bigger systems out of them. So the fifth idea in Clojure that I want to talk about is protocols. And the idea behind protocols is that they are a named set of generic functions. This is the path to polymorphism. So you define a protocol, it has some named functions here. Bar takes 2 args, baz takes 1 arg. So at a certain level, this is roughly equivalent to an interface in Java. And simple usage kind of even reinforces that notion. So here I'm defining a new type bar that implements that protocol. I can then create an instance of bar and call methods on that protocol. But I can also extend protocols to pre-existing types. So here, I call baz on the string A, and I'm told, well, you can't do that. You didn't define an implementation of baz for the string A. Okay, fine. I'll go back and define the A protocol as working with strings. If you're a Ruby programmer, right now you're grinning and going, I get it, it's monkey patching. Right? We're gonna stick things back in to the implementation. The important difference here is that in Ruby monkey patching, there's 2 places, right? There is the code that you want to monkey patch, and then there's the interface you want to inject into it, and you actually stick it in there. It's this icky, mutable transformation. And if you've done Ruby programming for a while, you may have hit the situation where you monkey patched something some way, and somebody else monkey patched the same name a different way, because you're competing for that name, right? There's no namespacing inside. In protocols, there's actually 3 places. There's the data or the object you're talking about, there's the protocol, and then the binding of them together is done in a separate place. And that separate place has its own namespace. So there's no danger of collision, and there's no mutable yuckiness. Now, let me just... So, I apologize for the dark slide. The 6th thing I want to talk about is ClojureScript. ClojureScript is a dialect of Clojure that compiles and runs in the browser. So, a few minutes ago at the start of the talk, I showed you the most interesting feature of the Go programming language, which is Go blocks. That was actually ClojureScript running in the browser. So, it's a slightly incorrect thing to say, but essentially, Clojure brings concurrency and thread semantics to browser programming. Likewise, the quote-unquote JavaScript framework that I showed you that worked with immutable values, pedestal, that allowed you to have reproducible results when doing client-side development, that is also, in fact, actually a ClojureScript-based library that takes advantage of the characteristics that I've talked about here. ClojureScript has terrific performance, so you're not trading off. One of the things you don't want to do in stepping away from JavaScript is step away from power and control. And ClojureScript provides fine control over the JavaScript generated. In fact, perfectly fine control if you really need it and want it. It also is devised to target the Google Clojure compiler for whole program optimization. And so a lot of times you will see ClojureScript programs optimized down smaller than similar programs written in JavaScript, even when you include the ClojureScript supporting library. The other thing that ClojureScript lets you do is a thing called the browser-connected REPL, or sometimes in slang, the BREPL. And the idea behind the browser-connected REPL is that you can actually work from Emacs or VI or wherever you like to work in a REPL and have the side effects happen in one or even in browsers. So imagine dynamically setting up 6 different browsers you care about, having all of them monitoring something, and then connecting a REPL simultaneously to all 6 of them and causing side effects to happen interactively. Provides an extremely fast way to try things out. So the 7th thing I want to talk about is reducers. And to motivate reducers, I'm going to talk about a scenario. I'm a pie chef, and I want to make apple pie. And the apples that are delivered to me have 2 problems, potentially. One, a lot of them have stickers on them. They have little stickers that say, what place they came from or whatnot. And a second problem is that some of the apples are rotten. And so what I do is I set up 2 conveyor belts, and I hire 2 helpers. And one of the helpers' jobs is to look through the apples and see which ones are rotten, and he throws them over his shoulder into the trash, and then puts the good ones on the next conveyor belt. The second helper's job then is to peel the stickers off as fast as he can and put them in the bucket so I can make pies. And you can do that just by composing sequences. So this is what that would look like in Clojure code. Take the apples, filter on the edible ones, and then map dissociating off the sticker. So filter the ones that I want to keep, and then rip the stickers off the others. And then I'm not going to actually make a pie here. I'm just going to count them up just to verify that I did the work. Now, the problem with that is, from a functional programming perspective, I have these 2 conveyor belts. And those 2 conveyor belts actually represent memory allocation, right? They actually represent work and effort. And so what I would like to be able to do is to say, I want to go higher order. I want to say, instead of hiring 2 guys, I want to go to my mad scientist lab, and I want to merge those 2 guys into one guy that does the work. Right, so I'll take the left-hand side of one and the right-hand side of the other, and it'll be a gruesome surgery and sort of like late-night movie kind of thing. And then we stick those guys together. And I want you to watch how the syntax changes when I do that. Instead of filter map count, I get rfilter, rmap, rreduce. And so this is just doing, one level higher order programming and saying, instead of composing the conveyor belts together, compose the functions together. And so this gives you a small performance win. But the really big win would be to observe that this job actually could be done in parallel. And so what you can do is, instead of saying filter map reduce, you could say filter map fold. And when you say filter map fold, you get automatic parallelism implemented via Java's fork join framework. So this is automatic parallelism, uses all your cores. If one core finishes a job ahead of the other core, it automatically does what's called work stealing. So the core that finished early can go back and get some of the work that one of the cores was lagging. And you can see what happens to the structure of your code when you want to make it faster or take advantage of multi-core. Right? The shape of your code doesn't change. You just drop in a different API. The 8th idea I want to show you is core.logic. And I'm going to show you via rock, paper, scissors, lizard, Spock. So this is an implementation of rock, paper, scissors, lizard, Spock in core.logic. Core.logic is an embedded DSL in Clojure, available both in Clojure and in the browser, that gives you access to logic programming a la mini conren. And so what you see here is really kind of in a nutshell the difference between logic and functional programming. These relation slots, winner verb are variables, paper is set as a constant. You can change the order of execution by picking which things you bind. And that's really the power of stepping up to logic programming from functional programming, right? In functional programming, I have to choose inputs, because if I show up without my inputs, the function's going to say, hey, you didn't give me anything. But with logic programming, I can choose at runtime which things are the inputs and which things are the outputs. The ninth idea I want to show you is the Datomic database. And because of time, I'm not going to actually show you the Datalog query language. I'm just going to show you the entire API. So you can connect to a database with different choices for storage protocols. And then here is the super important step from which all else flows. You can grab a lazily realized value of the database from the connection at any time. So when you query, you're not actually querying against the connection, you're querying against the database. And in fact, the query runs in the address space of any process you want. Because the database is an immutable value, there is no one process that's better than any other. So where you're traditionally used to thinking about going to the special place where the database does queries, there is no special place anymore. And special places are bad, right, if you want to scale and you want simplicity. This also means that you can do cross-database joins. It also means that you can join with in-memory collections and do logic programming against your own collections. The other thing that it means is that there is no infinite series of make up a class that represents person and make up a class that represents order and make up a class that represents order line item and so forth. Instead, there's a single generic interface called entity. And because the database is lazy, once you have that in hand, you can pivot in any direction you want and go anywhere you want in the data, as if it were a graph database. On the transactional side, provides ACID transactions. Transactions are functions of data. And the return value of the transaction actually gives you the entire value of the database before the transaction, the entire value of the database after the transaction, and the change that happened. Try building something like that with Active Record. Let me know how it goes. You can also back up in time. So take the database as of 6 weeks ago and then start querying against that. Or you can go into the future, or as I like to say, one possible future. I don't know tech stuff. But you can go into the future and add data to a database and say, what does a database look like if I did this without doing it? You can also get a panoptic view of all history of your data. So show me a conflated view of the present and all possible pasts and run queries on it. And you can monitor all changes in the system on a queue from any process. So you can say, from this process, I want to see all old values of the database, all new values of the database, and all changes. This is the way to make systems with reproducible results. And if you don't have immutable values, you're not going to make systems with immutable results without great pain. And the 10th idea that I want to talk about is Clojure's core async. I already showed you this. I showed you running multiple threads in the browser, so I'm not going to show you that again. The only thing I'll mention briefly, as we are short on time, is that core async includes a function called alt. If you're a low-level Unix programmer and you know what select works, how select works, this is select on steroids as a library that runs anywhere. I'll say that again. It's select on steroids in a library that runs anywhere, including in the browser. And the example that is used with the Go programming language is repeated here. This is a program that does a multi-threaded search that's broken into 3 multi-threaded sub-searches with a timeout policy. It's exactly the example that Rob shows for Go, except this is written in Clojure, and it can be run in Clojure on the JVM, or it can be written in Clojure on JavaScript. So, there's 10 big ideas. If you look at the ideas that I've told you about today, then 2 of them, protocols and targeting different platforms like Clojure and ClojureScript, running in different places, are things that any language could take on, right? And have taken on, right? Other languages have these kinds of capabilities. All of the other ideas, the things below immutability in this picture, so the unified succession model in refs, and Eden, the data language, and core async, and core logic, and Datalog, and Datomic, and Seqs, and reducers, all of these things either don't work at all in a language where mutability is the default, or are substantially harder to do in a language where immutability is the default. So if you're going to take away one message from this entire talk, it would be this. I do not know what the default programming language will be in 2020, but I guarantee that immutability will be the default in that language. My name is Stuart Halloway. I thank you very much for your attention, and I hope I'll speak with some of you outside. Thank you.